Welcome, everyone, to MFC Group's FasTech Seminar Series hosted by EAS Sales. Thank you for joining us. Today, we're spotlighting SimSurfing, Murata's simulation tool for passive component selection. Our speaker today is Bart Vodovich. Bart is a senior sales engineer at Murata, supporting customers and distribution partners with technical product selection and design and support across Murata's portfolio. Everyone is muted, so please type any questions you may have into the meeting chat. We'll monitor the questions throughout the presentation, and we'll make sure to answer them all at the end. And please do stick around to the end for a fun round of trivia, where our top 3 winners will win a prize. Now I'm excited to introduce Bart from Murata. Bart, I'll turn it over to you.
Awesome. Thank you, Robin. Okay, so good morning, everyone. Thanks for having me today. So I'll be walking through Murata's SimSurfing tools and then hopefully help show you how you can do more optimized component selection and design. And I do want to thank Mel Foster and EAS Sales for helping host and organize today's session. So speaker introduction, Robin kind of went over everything, but quickly add on some more details. So I'm a senior sales engineer with Murata based out of our Chicago, Illinois office. So I have over 4 years of supporting Murata's full product portfolio. And then I work closely with our various internal Murata product FAEs on application support. And then I specifically support customers and distributors across the Midwest region. So you can kind of see the map there. And today I'll be walking through the SimSurfing tool, showing how it can be used to quickly find and evaluate different components based on real operating behavior rather than what you just see on a data sheet. So before I get there, I do want to do a quick overview of Murata's portfolio. So as you can see here, we support both active and passive components, which I'm sure most of you are very familiar with. And then on the active side, we support things like wireless modules with Wi-Fi, Bluetooth, LoRa, cellular, UWB, and then sensors, MEMS devices, pressure sensors, MEMS sensors, PIRs. And then closing out the active section, we do offer power solutions, both AC to DC, DC to DC. And then on the passive side, you obviously know us for our caps, MLCCs. We support inductors, RF components, and EMI suppression products. So from that broader portfolio, narrowing it down on where SimSurfing will help, I kind of display it here. So while SimSurfing supports multiple product categories, it's especially useful for passive components, where you can understand how parts behave individually and in certain applications. So that'll include caps, thermistors, timing devices, EMI suppression products, mainly ferrite beads, common mode choke coils, and then inductor products, RF inductors, and power inductors. So when it comes to passive components, there are a few common challenges that you might run into. First, there might just be too many part options, which makes it difficult to pick the right one. And then even once you narrow down those options, the data sheets might not reflect real world behavior, especially when you factor in things like DC biasing for a cap or saturation currents for an inductor. So you kind of want to go over these specs and evaluate and compare different parts, which takes time. So setting up simulations can be slow and can be a bit of a trial and error. And then it could also be hard to compare multiple parts or multiple candidate parts side by side to see their relative performance across certain specs. So what you really need is a faster, more accurate way to evaluate components, and that's where hopefully SimSurfing can come in. So beyond SimSurfing, there are a large set of design support data that goes beyond typical data sheets. So S parameters, for high frequency behavior, especially in RF design, where you kind of want to look at insertion loss and reflection across different frequencies. SPICE models for simulating component behavior directly in circuit tools. EDA libraries for schematics and PCB designs to give you the symbols and footprints, CAE data for simulation environments, and CAD data for 3D models. So in addition to having all of this data available, we take our rich and abundant data and apply it to SimSurfing. So the design support data features firstly we have a lot of data available. So this is included in our S parameters, SPICE models, design libraries, and even 3D models. And then we have accuracy, so high precision in this data. So it's not only measured on performance, but also it's measured on performance and not just ideal values listed in the spec. And then dynamic models are available to where you can model for real operating conditions and not what's on a spec. So things like capacitance changing with DC bias or inductance changing with current, these are actually reflected in the data and then put into our SimSurfing software. So instead of static data sheets, you're working with more dynamic information. So a quick overview of the SimSurfing tool. So I'll kind of give overviews of certain sections before going into the live demo presentation. So at a high level, there are two main ways to use this tool. So at the top is the characteristics viewer, which lets you explore different components and component behavior directly. So things like I mentioned, impedance, frequency, response, DC biasing effects. You can compare different parts side by side depending on the part and depending on what you're looking for. And then below that are selection tools, which are more application focused. So these include tools like DC to DC converter design, noise filter design support tools, bias T inductor selection. If you're trying to do IC matching with a certain crystal, we offer reference matches for a clock to a specific IC, and then different thermistor performance simulators as well. So instead of just looking at individual components, these tools also let you evaluate how these parts behave in a real circuit or application. And then before I go on further, I do want to briefly go over the characteristic viewer and kind of what you'll see when you first open it up. So here you can see the real core part of SimSurfing, where you can go into specific passive component sections, pull up specific parts depending on the spec, and then further look at characteristic data and graphs. So for this example, RF inductor, which I'll go into in the live demo, but you can choose between the MLCCs, different types of caps, polymer caps, not limited to RF inductors. We have power inductors. And then on the EMI side, the ferric beads and common mode chokes. This kind of gives you a quick snapshot of what the tool is going to look like when you boot it up. And then for the selection tools, due to time, I will limit this and segue from portions of the characteristic viewer to mainly the DC to DC converter and also the noise filter design support tool, since those might be a bit more relevant. So starting off with that DC to DC converter support tool, I do have a little bit more about it before I jump into it a little bit later on. So this is one of the more practical tools because it looks at actual power supply behavior and not just individual component behavior. So you set your key parameters in this tool, and then you can select different inductors and MLCCs based on your operating conditions, and then it simulates how that converter will perform. So this helps you understand how different component choices can actually impact system performance, especially in a switching regulator. And then how that's going to look. So what the interface actually looks like, it's broken down into, or I broke it down into 3 different sections here. So at the top, you'll have your graph outputs where you can see results like inductor current, output voltage, efficiencies, transient responses. In the middle, you'll see operating conditions where you can set things like input voltage, output voltage, your switching frequency, your actual load. And then at the bottom, you can select between different inductors and capacitors and see how that affects your performance, how it might smooth a current or a voltage curve or improve your efficiencies. And then a quick note here, you can do inductor selection, but then you can also click over and do capacitor selection and see how that affects your either buck or boost converter. And then I will also cover a noise filter design support tool. So this is going to be used for designing EMI filters given specific frequency ranges. So instead of selecting individual components, this helps you recommend, or this helps identify and recommend filter solutions based on your circuit conditions and also target noise frequencies. So looking at it from here, so at the top, just like the DC to DC tool, you'll have your set conditions, which includes things like target noise frequency and operating parameters. And then once you put those in the center, you can build your filter topology either from scratch or from circuits that are already recommended within the tool itself. And then once you click that optimize button, it'll spit out different part numbers and recommendations, which you'll see in the C block there. So it'll recommend components based on those conditions. And at the bottom left, then you can see your different insertion loss versus frequency and see how effective your filter is, how well it's attenuating across that frequency range, given a certain circuit type and part number listing. So, and also in the bottom right, you can see mounting area and size layout information. So say you want low profile ferrite bead or cap, then you can specify that within the tool itself as well. And then at the bottom right, it'll show you the full layout or size of the circuit. So this helps you target a noise frequency and then build a filter around it to match it. And then it's much easier than actually physically building it or maybe using some other tools. And then a quick mention to our IC timing device search tool. So this one will be used to match certain external clocks or timing devices to a specific IC. So this is good for selecting Murata crystals or ceramic resonators based on a specific IC you might be using. So within the tool itself, you can search for IC manufacturer or the part number you're using, and then it'll spit out an associated Murata crystal or resonator that's matched or on the reference design to that specific IC. So it's better illustrated here where you can do your search inputs and then put in your IC manufacturer, IC part number, and then it'll spit out recommended timing devices from Murata. So in a lot of designs, timing components aren't one size fit all, so you do need to match them to specific ICs. So instead of manually going through data sheets and trying to figure that out, we offer this tool where you can put in these parameters, and then from there it returns a compatible timing device option along with recommended configurations for that part. So it takes out a lot of the guesswork, and this is a useful tool if you're doing that type of part selection. And then relevant parts, it scans through, so anything from 4 to 50 megahertz, depending on the IC, whether it's an MCU or a Wi-Fi IC or Bluetooth IC that might need an external clock, then this helps you narrow down on a specific Murata part. And then there are a whole bunch of other tools, which due to time I might not go over, but I will jump back here towards the end to review other of some more of these supporting tools. But the main focus for me is going to be the part selection, characteristic viewer, and then tying that to this DC to DC converter design support tool you see at the top, and then the second one, which is the noise filter design support tool. So with that, I'll stop sharing this and start sharing my window for the actual SimSurfing tool. So let me pull that up really quick. Okay, hopefully everybody can see my screen here.
It looks good, Bert.
Awesome. So this is the actual SimSurfing tool. If you just Google Murata SimSurfing, it'll be the first thing that pops up, and then you can easily get into this window. So for the sake of this, I'll start with MLCCs in the characteristic viewer. So let's click on over to MLCCs, and then here you can see, once it loads up, a full part number list of all our different caps. So you'll see all available MLCC options along with their specifications. So if you're looking for a part number, this is a nice way to look for a specific part rather than going through our product search on the website. So all your different parameters for an MLCC are here. And then you can pull up associated DC bias curves, capacitance over temp, temporize, capacitance over AC voltage characteristics, different Q factors, inductance, S parameters. And then if you have a part number you like in the product detail, that'll kind of take you to the actual product page on the website. Stock check, so if you want to buy samples or you want to check out the stock situation, you can click on this and it'll give you the stock scenario for any given part. And then you can download SPICE models here and then S parameter data and whatnot. So actually demonstrating the tool, let me just go through here and pick out, so let's go do consumer equipment, let's do in production. For the sake of this example, let's do a 10 mic part. Rated voltage, let's do a range, so let's go 6.3 volts up to 25. For dielectric, let's do X7R. And then I'll leave case sizes alone for now, just for the sake of this demonstration. Let's do 20%. So here it pulls up various MLCC options given the parameters. And say you want to look at this 6.3 volt part and you want to look at the DC biasing effects. So then you can click on here and then open up your associated graph and look through the actual characteristic data live at different voltages. So you can kind of toggle in and see, okay, so at 3.3 volts, what's my actual capacitance against DC biasing effects? And you can see here you get about 7 mics. At about 1 volts, you get the full 10 mics. So say you want to compare different parts. So you want to compare this 6.3 rated volt part to maybe this 10 volt rated part and this 25 volt rated part. So you can click Control and then click on the selected parts, and then you can do graph overlays of all parts given here. So this will give you part comparison data. And then as you can see here, DC biasing effects change depending on the rated voltage of the part. So even though all three of these parts are 10 mic parts, you can see that the voltage, as the voltage increases, the capacitance drops significantly. So this gives you a nice way of comparing different parts if you're looking at different part options. Because with the cap, as you all know, it's just the internal structure, the dielectric used can affect DC biasing. MLCCs are just stack layers of ceramic dielectric and electrodes. So for class 2 dielectrics, since they are ferroelectric dielectric, they're sensitive to electric fields, and they get DC biasing effects, which matter. So you kind of want to view these in a more a friendlier way than looking at a data sheet. So that kind of gives you an idea of how useful this tool can be between both comparing parts and looking at specific characteristic curves that matter to a specific part. So for this example, an X7 cap, you want to look at the DC biasing. So you can easily compare and look at that here. So that kind of gives you a good idea of how to use the characteristic viewer. So that was for MLCCs. And going back to caps, I guess, you can also toggle for different dielectrics and whatnot and view those curves as well. Other ceramic cap technologies, so we have the 3 terminal caps, mainly used for EMI filtering applications. You have these leaded ceramic caps, resin molded caps that you can look at as well, depending on your application. Beyond ceramic technology for capacitors, we have these polymer caps as well, which are good for bulk capacitance, and they exhibit no DC biasing effects. So if you're looking for a tantalum replacement, we do have these. For example, I can pull up a DC biasing curve here for this, and you can see it maintains its capacitance of around 470 mic across the full rated voltage. So you can go through and do part selection, but then also view these characteristic curves, which might matter to your design. So that was the cap section. Now let's jump into, say, the RF inductors. So like with the caps, where DC biasing mattered for class 2 dielectric, for an RF inductor, you're worried about your SRF, self-resonant frequency. So you might want to look at parameters or different overlay graphs to determine that SRF to maintain that it'll work as an inductor up until that frequency. So for the case of this example, let's do, say, consumer equipment, general product. Let's do, let's say, maybe 47 nanohenry. Let's do, leave the tolerance alone. So you're looking for 47 nanohenry part. Maybe let's do 5% to narrow this down a little bit more. And then here you have different parts depending or given those parameters. So 47 nanohenry part, 5% tolerance, and you have all these options. So you want to find out, okay, what are the self-resonant frequencies for these inductors, since that might matter to my tuning circuit or application. So you have all these options. And then you have these different part number suffixes, or actually different part number starts. So these LQWs are wire-wound RF inductors, LQPs are film type, LQGs are multi-layer. So depending on the build of the RF inductor, you might get different characteristics as well. So with the wire-wound RF inductor, you might get better Q factors. Your self-resonant frequency could be very far right or into the high gigahertz compared to maybe a multi-layer type. So for this example, let's compare a multi-layer, a wire-wound, and a film type at this 47 nanohenry. Let's do up to 20 gigahertz up here, so we get the full range. And then let's pull up impedance frequency plot for these three different parts. In this case, there are 4, so I think I toggled one on earlier. But here you can see that the wire wound has an SRF that's farther right than the film and the multi-layer here. So this is a nice way of, okay, so you're looking at 47 nanohenry parts, but you want to look at key parameters or specifications. And then this lets you or allows you to view that very easily. So then say you want to do another graph. So to overlay multiple graphs on one screen, got to click the multi-graph, and then you can pull up the Q factors. So let's expand this a little bit here. Oh, it's stuck. Close out. Let's try to open it up again. There we go. So now here you can see the Q factor of all of these different RF inductors. So like I mentioned earlier, the wire wound's usually going to exhibit higher Q factors, which you can see here. The film type usually has good Q factors as well, but they're made to be very small. So it won't quite be as good as this wire wound. And then the multi-layer is kind of a catch-all. Usually it's the most cost-effective type of RF inductor. So depending on the part, depending on the size or the inductance, it's good to check through either different types of RF inductor builds or just different types within the same family and just comparing SRF response or Q factor response, which is very helpful. And going on to power inductors. So here, what we're going to be worried about is going to be saturation current, where your inductance drops with applied current or higher applied currents or applied current. So let's do consumer, let's do general, let's do in production. And then for the sake of this example, let's maybe do 10 microhenry. Let's do rated current and saturation current to be above an amp. And then here you have different options. So just like with the RF inductors, you do have different builds with the power inductor. The core could be a ferrite material, which is used to give you higher bulk inductance, but then it also exhibits higher saturation with applied current, so that effective inductance will fall off a cliff, just like with DC biasing effects on a capacitor. So let's look at maybe this inductor here. And you can see here the saturating across the rated current. So as you go into a higher load, your effective inductance drops. And this gives you a nice way to view that interactively. Then let's click on one of these metal alloy inductors, which exhibit a bit less of a drop over that affected rated current. So it's a nice way to do or look at your effective inductance as opposed to what's written on the spec. So all these are 10 microhenry, but depending on your circuit criteria, the effective inductance will be different. So this actually is a good segue into the DC to DC tool, since that will kind of tie in MLCC and power inductors, which I just went over. So once you go into the main page, scroll down, you'll see this DC to DC converter design support tool. So as I mentioned in the PowerPoint, kind of have your three main sections here, and you can play around with different inductor or MLCC values with a specific buck or boost converter to see how that either smooths your voltage, affects efficiencies, smooths current. So for this app or for this example, let's keep this at 3.6 volts. Let's make this maybe 1 volt. Maybe do higher current. Let's do switching frequency of 1 megahertz. And so parameters are set. I'll leave this modulation as is. And then here we can look at, say, a 1 microhenry part selected, but it might not match our rated current. So let's do saturation current, and these to be above that 1.5 amp. And then let's say we want the size, or say it's a battery operated application, maybe it's a wearable, and you want the height to be a bit lower. So let's do maybe 1 millimeter max height. So here you can look at parts given the key criteria of your buck converter, and then you can toggle down on size or case size. But for the sake of this example, so we have that 1 mic, let's toggle off of that. So let's have this 3.3 microhenry part. Let's do this 0.47 and this one. And then you can see different overlays on which inductor you chose and how that affects your smoothing on current here. So higher inductance, you see fewer ripple. And then for output voltage, if we go to the cap section, say we want, so here it automatically used a 22 mic part. Say we want to use higher capacitance to smooth that voltage a bit more. So let's go down, or up rather. We have some higher bulk capacitance here. So you can see, let's go and check for ripple. And you're getting about 4.7 millivolts a ripple. And let's change this to maybe 200 mic parts. And you can see here the ripple went down a bit. So you can kind of interactively select different cap inductor options given your buck or boost design criteria, and then check how that reacts on these interactive graphs, which is very helpful. So those inductors, power inductors, MLCCs segue nicely into the DC to DC converter tool. Next, I'll go into some of our EMI suppression filters, mainly ferrite beads, common mode choke coils. For me, this tool has been extremely helpful with finding a correct ferrite bead or filter option. So for this ferrite bead section, very similar to the other characteristic viewers. So you can see all your different ferrite bead selections. For the sake of this, let's narrow it down to general product in production. Let's say 600 ohm at 100 megahertz. And then I think I'll leave everything else the same. So the thing with ferrite beads is that they try to standardize it to where the impedance is listed at 100 megahertz. But say, for example, your noise is at 200 megahertz, and you still have to pull up the curve and see how that impedance plot looks over the full frequency rather than just at 100 megahertz. Because for all these different 600 ohm parts at 100 megahertz, the impedance might drop off sharply right after, or maybe the amplitudes are different, or other peaks are closer to 1 gigahertz rather than maybe 500. So you kind of want to look at these a little bit more closely just to validate. So here I pull up 4 different ferrite beads, and here you can see different impedance plots for those 4. Let me try to pull that up again so I can expand it. Yeah, sometimes it glitches out a little. So let me just restart that. Let's do 600 ohm again on this criteria. Let's compare, let's say, these 3 parts. Now I can expand it a little bit so you can see it. So as you can see, these are all 600 ohm at 500 megahertz, which you can see here, but then they all exhibit different impedances after that. So this one, for example, you get very heavy impedance at around 600 megahertz, and then some of these follow similar impedance plots. But yeah, so this is very useful for actually viewing the full impedance over frequency range of a ferrite bead that might not be on a data sheet or is very unclear on a data sheet. So this gives you an interactive way to check for impedance at a specific frequency. So it's very helpful. And to make that a little bit easier or even more helpful, that's a good segue into the noise filter design support tool. So again, it'll be down here. It's next to the DC to DC one. So here, like I mentioned before, you can kind of set your criteria and then try to match a bead or a specific filter topology to a certain noise frequency. So for the case of this example, let's do maybe 1 amp. Let's do 50 volts. Let's make it a non-automotive application. And then it kind of gives you target noise frequencies here. But you can also do your own. So for the sake of this example, let's do maybe 200 to 600 megahertz. You have noise and you're trying to filter for noise or attenuate for noise in that frequency range. If you go down here, you can select different topologies that are already built in. This one being a pi filter, so let's do a pi filter for this one. Let's try to optimize, and it should load up 3 different parts here, dependent on your operating criteria and your target frequency noise attenuation range. So once that's done, it'll recommend a cap and then a ferrite bead to help you attenuate for noise within that frequency. So it gives you this S parameter chart here where you can kind of see you have very good attenuation at 200 to about 600 megahertz. So rather than going through and looking for different ferrite beads that match that, this kind of spits it out for you. So if you do, you can do multiple overlays of different filter topologies to see if they have better cutoff characteristics or stronger attenuation. So for the sake of this one, let's maybe just do a ferrite bead and then click optimize. So here you can see the ferrite bead on the top here in the orange, and then the pi filter here in blue. So you can see the pi filter has better attenuation than the ferrite bead listed here. So you can kind of compare different filter topologies and how they attenuate for noise. And then say we take that ferrite bead part number and then go back into our ferrite bead tool. We can kind of click it back into here and then validate that impedance right here. So you can see at about 200 megahertz, you have quite a bit of impedance, and going over to 600 megahertz. So the noise design filter tool is very helpful in giving you the right part recommendations in a very efficient way. So those two tools I find the most useful in my day-to-day usage, but given your application, you might find where some of these medium voltage capacitor selection tools, or you have a thermistor design where you're trying to test for performance, or you're trying to find the right inductor if you're doing a PoE or some type of power over signal power line combined into one where you're looking for a biased T inductor. It's another tool that's here. So the main demo for today is just the characteristic viewer and then how that ties into some of our selection tools for more optimized part selection. And then I'll stop sharing this and quickly go back to my presentation. So summary of supporting tools, we went over the DC to DC converter tool, which helps check for inductor loss and efficiencies. And you can optimize different combinations of inductor or cap depending on your circuit. Noise filter design support tool, which helps you do different filter topologies to optimize for specific noises at specific frequencies. So the bias T inductor tool, I didn't go over. But if you are working on a power over coax application where you're combining, say, DC power and RF signals onto the same power line, it can help you optimize on the inductor selection based on either the signal transmission speed or different parameters. IC timing device search tool, which helps you kind of dedicate a specific timing device to a specific IC you might be using that requires an external clock. Medium voltage capacitor tool. So say you're working on a higher power or resonant application where an MLCC can see a lot of AC stress. So you want to verify whether the part can handle the high voltage, high current, heating conditions safely. So this covers MLCCs rated over 250 volt. And then for our thermistors, so for our negative temperature coefficient NTC thermistors, we have a performance simulator. So this is used for temperature sensing or compensation applications. And this allows you to simulate how resistance changes with temperature given a specific circuit. And then for the positive temperature coefficient thermistor, we do also have a performance simulator where you can test for things in, say, a protection application where you want to see current limiting or resettable fusing specs on a specific PTC where resistance increases under faulty conditions. You can kind of easily visualize that within this tool. So that was a quick summary of the characteristic viewer as well as different supporting tools beyond that. And I think the main takeaway is that each of these tools helps move you from individual component specs to, say, real application behavior. So with that, that's all I had for today. So I want to thank everybody for your time, and I'm happy to take any questions. So I guess I'll toss it off now. So thank you.
Bart, thank you for that excellent presentation and demonstration. We do have one question. How does the DC to DC component selector tool for Murata compare to an IC supplier specific tool like ST, Texas Instruments, or ADI?
That's a good question. I think in my case, I'm maybe not as versed in those, so I can't give a direct reply, but I can go to our power division and maybe check and cross-reference how ours compares against, say, a ST or a TI. So I can follow up on that after the meeting.
That would be great. And we can send that feedback when we send the recording.
Okay.